So again, thank you for being here despite this nice weather. And I am very amazing to do this exercise of a recording that I prepared for everybody. So it is so my pleasure to show you methodology characterization of crystals, and especially nonlinear crystals. So of course I will not review all of them because you will see how much they are in quantity, but I will focus on main that I will precise now, okay? So the outline of my presentation will be first, of course, remember our fundamentals. We have to have that in mind when we are in experimental rooms. Of course, not all the equations that have been shown to you during the lectures, especially in the first one that you have in the first week. But however, we have to have in mind many things before beginning to run experiment, especially not to make mistakes. And the second point will be the design of and the material issues in nonlinear optics devices. Knowing that, I will come very quickly to the third part, which deals with the crystal optics, because my talk will be essentially devoted to crystal optics. And then two main questions come very quickly when dealing with the characterization. The first one is how to determine phase matching direction, and the second one, the direct measurement of the walk-off. This is the first part, they are connected, and then I will speak about the difficulty of determining the nonlinear coefficient value and sign when dealing with the gain. And finally, I will come to the orientation and shaping of crystals, which is very important before performing any characterization. I will show you which devices we need to be very precise in this action before dealing with experiment. And then I will speak about one specific problem, because when we deal with optical properties, we work in the dielectric frame, and everybody has been exclusively speaking about this frame. However, when we prepare samples that will be oriented, this is done in the crystallographic frame. And it happens that in low symmetry crystals, it is not so easy to connect these two frames. And finally, I will discuss about the step between characterizations and the new devices. So first, remember the fundamentals. So you will agree that we saw that together many, many times. Okay, so I will try to explain why I come back to them anymore. So since we are interested in applications, of course, we will focus mainly on the second order susceptibility, so second order development of the polarization. But since we will have to propagate in crystals, we have also to understand and to take into account the first linear order of the polarization, which is the first step we cannot cancel, of course. But we have also to deal with it a lot, especially when we are working with crystals. However, what I will show here, but I didn't want to make a catalog. However, what I will show as characterization techniques could apply immediately to the third order of polarization. I will not show examples, but we have many publications dealing with the Chi-free concerning the characterization of a crystal for optics. Now, when we limit our discussion talk to Chi-2, then many possibilities can be used for the characterization. So first of all, we have to know what is the transmission of the crystals, because of course we are not dealing with device. We need for characterization. That means that we want the ID of the crystals that we are studying to give that to people who will use these crystals. So first of all, we are interested in the transparency range. And this will determine the difficulty of our characterization. Of course, if the transparency range is limited, then we can have simple lasers with limiting tuning or limited emission like neodymium lasers and other lasers in the visible. But recently, it has been shown that new crystals like to have a very large range of transparency, and then we will have difficulties. That means that we will have to use, if we want to characterize these crystals, all possible conversion processes. So if we deal with second harmonic generation, we know very well this fusion of photons process, but we will have to take in mind when making characterizations that this means that if you input a laser wavelength, you will only get this characterization at half the wavelengths. So if you want to tune the properties within the transparency range, then you see how it will be difficult, because each time you get one, you get half the wavelengths. So we know that we have a more general scheme, which means that we could input 2 different wavelengths in the crystals, but this means then 2 different lasers, and then we have more possibilities. And dealing with some frequency generation, however, if we input 2 wavelengths, we will get the sum of it. And with this process, we will increase the frequency and then decrease the wavelength. So this is suitable when we want to know what's happening in the crystals concerning frequency conversion, especially in the low part, which is here in the frequency, in the low part on the transparency range. Of course, many people spoke about the spontaneous down conversion of 2 photons. This is suitable so that when you want to know what happens when photons are created in the upper part of the transparency range. But we know that when we deal with characterization, if we want to study this process directly, only few photons will be generated, and then we should have very special devices for recording the signal. And then we prefer, for characterization, to do a simulated down conversion of the 2 photons. And then in my presentation, I will speak a lot about, difference frequency conversion from these 2 schemes. And then the only limitation, of course, is now the upper part of the transparency range when we speak as a function of the wavelengths. So we have all the fundamental in mind. Benoît Boulanger lecture of many pages could be used after this school if you want to know all the details. So I will focus, on these main properties. What is important for us is the energy conversion values. So since we always, 2 of those frequencies are known in our experimental rooms, because for SIG they are the same, for SFG or DFG we use 2 lasers, then this one is fixed each time we run the experiment. I mean, one of them. And then what is important is when we want to know if a crystal is very potential for an application, we want to know the phase matching conditions from the phase mismatch, and I will consider the collinear picture here. And also we want to know what are the phase matching conditions. So what about the design and the material issues in nonlinear optics? So Majid developed a lot in the first week, the design issues. So what I'm going to show now concerning the characterizations will apply to any kind of device, OPO, OPG, and OPA. Of course, when people spoke of device, the efficiency value was very important. High gain was very important, but when doing characterization, I will show you that, remind you in fact, that the parameters are the same even if you work with high gain or low gain. So of course, when you receive a new crystal which is unique, and you don't know because the growth process is not yet developed, you don't want to destroy it. Of course, in the characterization, we will deal with low gain. But all the results I will show, of course, will be suitable for all those devices. So Marty Fire accepted that I showed this slide. And I like it because you can figure out how many material issues you have to determine when you want to put a crystal in a nonlinear optic device. So I don't make a list. I just want to tell you that I will focus on the basic nonlinear optical properties. So it will include phase matching or quasi-phase matching angles. I will be interested in the nonlinear coefficients. Of course, because I told you that when doing nonlinear optics, we also have to deal with linear optics, I will speak of the spatial walk-off. I will not give the characterization of the damage threshold. However, this is the first thing that we do in our team before making characterizations. Of course, not to destroy these samples. I will also discuss about the angular and spectral acceptances. And what we do, we work for application. So, of course, the first thing, as I said, is to determine the transparency range and, of course, not to deal with absorption. So, this, from that, I can give you the targeted properties in this talk. So this deals with phase matching conditions from birefringent phase matching, also quasi-phase matching or angular quasi-phase matching. So I will speak about phase matching directions determinations that could be that could correspond to non-critical phase matching or critical phase matching. I will discuss about the determination of nonlinear coefficients, but also associated conversion efficiency, angular and spectral acceptance. And as I said, I have to deal with the spatial walk-off, so we also determine this property. What I am going to discuss here could be, of course, made at any temperature, but I will limit my presentation to the room temperature for the characterization. So, phase matching conditions, if we want to make a characterization, let's focus on what we have to determine. So, we have seen many times these equations. Let's remember that there are many parameters that are involved. If I keep on the corner the temperature, we still have the frequency, the angular frequency. We have the angles that are marked out in the dielectric frame. From the theoretical point of view, people like to discuss with this parameter, but in the experimental room, classically, we will go to the wavelengths. Okay, so when we deal with phase matching conditions, we want the angles, theta and phi, we want the wavelengths, like shown here, and that means that we have to solve these corresponding general equations. So here, I didn't consider any special material, could be any kind of symmetry of material, of course. And here, this parameter I will show in detail, it means that it could include any structure that was performed in the material. So what is important is that material directions are governed by the linear optical properties. So it is interesting because you want the nonlinear optical properties, but in fact, you have to focus on the linear one. So now let's come to the gain and the other targets. So the gain, of course, as I said in the devices, it is important to speak of high gain, but Majid showed the following equations, and we see that even if we work under low gain through a material of L length, then we have an equation showing the same parameter gamma that is very important for the characterization. So as you see, we have to deal with the input power of the beam. We have to deal with the linear properties through the dispersion equation of the main indices of the material at the different wavelengths that are concerned, that are involved in the parametric process. We have also to deal with the wavelengths, but also with these chi effective coefficients. So if you come back to Benoit's lecture, for example, you will see, so they are the parameters from the material that are the chi2 coefficients. They are given by the material himself. We have to find them. But also we come back to the linear properties through the polarization state of the field of the free involved waves when we are dealing with a chi2 process. So still, when dealing with the nonlinear coefficients that are given by these elements of the chi2 tensor, we have also to deal with linear optical properties, especially with the polarization states of the free involved waves in the process. And if we want to be sure that we are dealing with gain, this is a big issue in our characterization, we should not only focus on the gain conditions, which means that delta k is equal to 0 and that we have this following expression in the gain only. We should also look out around phase matching condition to check if we really have spectral acceptances, because this signature of spectral acceptances and means that here really you will have phase matching conditions. So this, I spoke of spectral acceptances, but they could be angular and also, of course, thermal, but I will not speak about that. So especially in our characterization scheme, we deal with angular and spectral acceptances. We can do that each time we are looking at the phase matching conditions, and this is the best way to be sure that we have phase matching conditions. So few selected issues compared to the large list that I showed in the beginning concerning the materials. I will also limit my talk to crystals. However, you will see how the issues are very ambitious and how we could overcome the difficulties. So now I will focus on crystal optics. So first of all, crystals have symmetries, as you know, so then we have limitations of the non-zero and independent element of the chi2 tensor, as it was shown in the lecture. So you have here the different 7 kind of symmetries, crystallographic symmetries that you can deal with. Could be cubic. I show many posters dealing still with cubic in quasi-phase matching materials. During a long time, there have been anisotropic uniaxial, which means high symmetry of crystals. But recently, we see more and more new crystals shifting to low symmetry crystals and especially monoclinic ones. So we have to have really in mind what kind of symmetry we are dealing with, and most of all, before speaking of gain, what will be the nonlinear coefficients. So as it was shown, only some non-centrosymmetrical point groups of crystals could be studied with chi2 when dealing with chi2. And what we have to know in mind that these crystals impose not only the values of the chi2 element, but also the sign. And it is very important when we work with gain, because the sign especially could change completely the result. Concerning the crystal optics, so we know that we deal with an index surface, and we have a lot of chance because this index surface is described by an analytical equation. So it is here are the solution of what we call the Fresnel equations that are given in the transparency range of the crystals. They look very complicated, but we can have in mind in the experimental room many simple ideas that help to make simple drawing and to do very quickly characterization. And what is important, of course, is that first of all, an important parameter is the direction of propagation in the dielectric frame. All possibilities could be involved through the theta and phi angle, and they are shown here in the solution through the B factor and through the C factor. And the other point that is very important if you want really to have this complete idea of propagation in these media, is to have the dispersion equations of the main value of the refractive indices. So you have to deal with 3 main equations in biaxial crystals and 2 equations of the principal indices in uni and axial crystals. And also, because you are always dealing with anisotropy, you see here that in the previous equation, I didn't add these signs, but in fact, there are restrictions in the two, because in fact, wherever you propagate in general in anisotropic media, the field will see 2 indices. And this means very much a lot of restriction concerning the solution of these equations. And again, I will detail in a moment, but everybody knows this special a term that corresponds to a structuration of the crystals. So the crystals imposes dispersion equations, in fact. This is what we have to have in mind. If we want to know what are all the possible phase matching conditions in the crystals, provided we work at room temperature, so we have to know the dispersion equation of the material. So when we are in the experimental room, no way to have these equations in mind. It is very, we have a lot of chance because we will deal with these corresponding properties, drawing of the index surface. So as I told you, any direction we will have two solutions of the principal refractive index because it is a second order equation that I showed before. So always two solutions, except along the optical axis here. There is only one for uniaxial. There are two possibilities for biaxial. And what I show here as the index values, the smaller one will be called n minus, the biggest one n plus, and also the same here. And this is a convention, of course, and associated to these mean values that are all in fact, the values that make the dielectric susceptibility diagonal, the dielectric constant diagonal, and also there are those main values, but they are also associated main vectors that are the two polarization states. So each time you select a direction, you have to deal with the two indices value and the two corresponding polarization state. I would like to come back here to this spatial optical axis because you will see how we are experimental condition. We could see, like the finger in the noise, this what happens when we propagate here in this situation. And we can use it to make many analyses. Okay, so I come back also to the field vector of interacting waves, and they govern the conversion efficiency. So if we limit our work to the principal plane, it's very great because we can take a pen and a book and we can calculate or even use a program if we want, but if we don't have the computer close to us and we need discussion, then it's easy to know these parameters of the polarization in the principal planes, and then we can figure out what could be the effective coefficients. Because what is important is that even if you have non-zero non-elements that are involved here, it is important that the combination of this element and the product of this, that I will call the field factor, doesn't go to zero, because otherwise what you will only do in the experimental room, you will increase the in-point beam and you will destroy the samples. Okay, and what you see here that is special is when you propagate here in this direction, there is always two refractive indices layers of the index surface. One is circular. It is so this one, in this case, the pointing vector, that is what you see, the light that I am sending here is the pointing vector, then correspond to the direction of propagation. However, if you select through the polarization that is horizontal this other layer that is elliptical, then you have to have in mind that then the direction of propagation doesn't correspond to the direction of the light of the pointing vector. And then here is the walk-off that people have been speaking about, and I will propose a characterization of this walk-off that limits the length interactions in the devices. So the walk-off, as I just say, reduce the length from this formula that you have here. So the walk-off here, you can see, means that if you send a polarized beam that could correspond from the polarization initial state that could solicitate this vertical and this horizontal component, then one beam that is in normal incidence becomes two beams from the pointing point of view. Of course, if you look at here, you are in normal incidence, and then according to the Snell-Descartes equations, normal incidence means the k vector is always like that, doesn't change. However, because of the walk-off, the pointing vector is like that, and then that means that the output of the crystal, provided you make a long length of crystal, you will see the effect of the walk-off. So the walk-off is has the particularity to behave like that. So it is shown here as this corresponding plane. And so people like very much non-critical phase matching because this is the way it is 0. Otherwise, close to 45 degrees, it will be maximum value. And just know that it is not symmetrical because from analytical equations that we can write in this plane. It has been presented in the theoretical lectures at the arc cosine between the vector D displacement and the electric field polarization state. But it is not easy, of course, to see this D vector in the room. So we will use this definition. We will check the walk-off. We will study a walk-off through the difference of direction between the direction of propagation of light and the direction of the energy. So P vector, pointing vector, and K propagation vector. So which material are concerned? Which material could apply in this talk? All you want, all crystals you want, in fact. So we have been applying methods for birefringent phase matching, which means that we use bulk crystals that are grown in different kinds of symmetries. And in this situation, in fact, we could still use this parameter and state it to the infinity because, in fact, this is like you didn't have any domains, so like the periodicity was infinite. Also, we can check crystals, use crystals that are quasi-phase match. This has been a lot of discussed during the school. And if it is quasi-phase match like this, only in one direction, then the effective coefficient, the parameter in the equations of phase matching will be a constant. Also, we could describe crystals with ferroelectric domains, which is a classical way of making phase matching, and deal with angular phase matching. We see now a device using this kind of configurations, and it has been proposed a long time ago, but now it really comes to devices, as Majid showed. And this has been patented in 2005 by Benoît Boulanger and his co-workers at this time. And dealing with a full cylinder or a partial cylinder, just because you don't need to use this if phase matching conditions are only in this part, you should better cut a partial cylinder. Then you will have the continuous tunability of the device in this way, which is very interesting. And here you see some kind of the historical, I will say, a device that have been proposed in that time in PPKTP. So I increased the symmetry. I've been working, dealing with one direction, two direction, and why not three directions with the general scheme of quasi-phase matching. So this is very interesting from the theoretical point of view, could be perhaps one day from an experimental point of view. So, and in this case, we have the complete 3D tunability because we can project our direction of propagation along any periodicity that is related that way to the real one between the domains. And in fact, I just wanted to show that long time ago, not with a phase match. It was not a phase match, this kind of crystals. It was a bulk. We did and succeeded in using a crystal cut that way in a cavity and make a laser, parametric laser. So now, how to determine the phase matching directions? So first, you come back to all the previous lectures. You have, I think, the equivalent of a big book. Just to say that after a small calculation with Benoît, we decided not to print all the PDF because we calculate that you will come back with heavy things in your luggage, and we know that many of you come from very far. So we have the chance that now we will have on the website all this book to work, to use. So phase matching conditions, now I think you've got the idea. So we have to know what are the dispersion equations. This is really what we have to know, and to solve these equations in this situation. So if you know this, then there are two possibilities. You know this, and then you put this here, because this is included in these equations that are the solution of Fresnel equations, and then you regard that way the solution you are looking for. This is what I will like the method. I will call the method one. Of course, this is true for all phase matching directions and wavelength, all phase matching process, BPM, QPM, 2D, and 3D AQPM. The other possibility, because this is really reversal, the other possibility, of course, is to deal directly with the angular and the spectral phase matching directions. And then, if you put that in the equations, you will determine the Selmayr equations of the crystals. So what is the interest? In fact, people are really fighting in the two ways of working a lot. And I would like to spend time on this purpose. So in fact, people want everything. They want the complete ID of the crystal for all processes and in the whole transparency range of the crystal. And unfortunately, right now, the transparency range, as you saw, becomes larger and larger and larger. So that means that we have really to deal with a lot of data. And so people will propose first to determine these quantities and to put here, and I will show, I will call this the method 1, and the other method is to determine this, to put this, and to get this. So of course, when you deal with that, we are not going to make all phase matching direction and wavelengths, all possible processes, SFG, SHG, DFG, for all kinds of situations. We have a strategy, and we need a strategy. And based on a good strategy, we could have all the information needed so that people, in fact, could use very reliable Selmayr equation, put that in their program, and know, provided they have the idea of one crystal, what can be done in any kind of device. So for the determination of phase matching direction, we fight between two methods, the computing approach or the direct measurement. Computing approach means, I say it again, that you have the Selmayr, the dispersion equations of the refractive indices. I remember that we know what is the index surface of the crystal. For example, if I deal with a uniaxial crystal, let's say it is positive. Remember, if I am in a YZ plane and I deal with the angle theta, okay, I know here what are the equations of the Selmayr. The only thing I need to know is when we are in this situation, if I know those two very important parameters, I have the whole picture of the crystal. And of course, if I deal with biaxial, this situation is completely the same. If I know at any wavelengths where are these values, but I'm dealing with nx, ny, and z, and also I will work in the following assumption. Then in this case, I am able to have the image of the index surface in the whole frame, whole dielectric frame. Then the first approach that comes in mind, because this is very easy to implement and everybody learned that at school, is to use the Prisma method. So the Prisma method means that you will cut crystal as a prism, as you see here, and you will use tunable light if you can. So, and this is a great challenge, in fact, because you should use tunable light over the transparency range, would be better. And you have to use also the two corresponding, the two possible field vectors that correspond to the two layers that you want to study, because by using this or this, you will select this index or this one. And then we know very well, I think everybody learned that at school, you will measure from the minimum of deviation, you will get the value of the index, principal index as a function of the wavelengths. The problem is that this is pictures for one wavelength, and everybody knows that we have refraction here. So that means that if you change the wavelengths, we have to be sure that we are dealing always with the same direction here, because if you want to reach these two values, you have to be sure, for example, in this case, that you remain propagated in sample along the y value. And this means that this prism has a spatial shape that should have the same angle here and here, okay? The other possibility that you will see is that people cut also half a prism, so that you don't have refraction here, so you are sure about your direction of propagation, and then you measure the minimum of deviation. And then the indices. So here is an example that was published recently concerning CDSCP2, that is a new nonlinear material. And you could see that here, in fact, they have been dealing with a long wavelength. And these are very good, in fact, experimental data. They took care about using maximum, not all, but maximum of the transparency range. And they recorded many points, especially where the variations were very important. You can do the same, of course, with biaxial crystals. However, with the biaxial crystals, the situation is more complicated because you need to have access to the free indices. So if I use, for example, this ax y, I could reach through a selection of polarization nx and nz. I am always in the assumption, the following assumption. Okay. But if I want, so I have 2 of 3 that I need as a function of the wavelengths. So I have to propagate, for example, along y. And the other solution that is possible, for example, is to propagate along x. And then I will have these 2 other values as a function of the wavelength. So 2 the same, but the third one that is missing is here. So that's why we have to use 2 prisms to be sure that we have a special shape so that we can propagate always in the same direction here, or use alpha prism, as I just drawn before. So here are all other data. These crystals appear to be transparent from 0.4, perhaps lower than that, but up to 2.7 microns. And you see here those data. I think the points are corresponding to the accuracy. And you see that the data were only recording in only a part of the transparency range. So this is the first approach. And from that, people get the Selmayr equation, the dispersion equation, no, the dispersion data, excuse me, first of the main values of the refractive indices. So then we put that in the phase matching equations, and we solve numerically or analytically. And here, for example, is an example of such a solution that was given in a crystal Y-cob for SIG type 1 in a plane YZ. And then you can see immediately that especially for these high wavelengths, especially because they didn't measure the refractive indices in this range, they couldn't get agreement with the measurement that we performed in our group. Okay, so we have to take in mind that if this experiment is easy, it's not accurate, it's not possible to have great accuracy if you don't take care about the way you measure those data. So it is shown, if I take a phase matching condition, if I change the values of the solutions from less than 1 degree, or even 1 degree, I see that I need a change in the refractive indices of plus or minus 10, minus 4 if I want such an accuracy. So that means that if I have, for example, a value that is 1.0, 4, and 5, I need this digit to be accurate up to this digit to be sure that such a simple method will give accurate results. Okay? However, this is the method that is commonly and generally used to determine the phase matching conditions of the crystal. Do you have questions? No? It's okay? We could go further with this to understand what really we deal with. I forgot my notebook in mind. So how are they connected, in fact? How are they connected? Young-like numerical solutions, of course. So you take your computer, you put everything, you get everything. But sometimes it's like a black box. So it's good to take our pen sometimes and to look at what is inside to see what is the challenge. Okay. In fact, so let's speak about type 1, SAG. So we have 3 wavelengths, lambda 3 that is generated, lambda 1 and lambda 2 that are income wavelengths. And because we are dealing with nonlinear crystals, this is the corresponding polarization state. And these polarization states are given by the main vector associated with the 2 refractive indices of the two layers of the index surface. So let's say, for example, I am in the YZ plane. I'm going to look what's happening. So these equations here, well, you are dealing with type 1. So in this case, I will have n minus of lambda divided, because I want to do SAG, this, minus n plus lambda. So I will draw this later, because I am limited. This minus this. And in fact, it is 2 times. I have to solve this. I am in a bulk. So in a bulk, I say that this is 0. Infinity. So this term, the inverse is 0. So then instead of that, you see that I can put, here twice this number instead of this. So in fact, when you simplify, you will see that if you want to make phase matching directions, that means that one of the index layer for the half wavelength should be equal to the other layer for the fundamental wavelengths. Okay, so this is what you have to do, and as it has been already said, that means that, in fact, if you draw the 2 layers as I did, for example, in the YZ plane, like that, this is n minus, this is n plus, okay? And if I am dealing with this solution, I have to involve their wavelengths. I should better draw them as a function of the wavelengths. This is n minus, this is n plus, and I have to find the solution. I have a solution if I found the same value for this and this. So this I cannot know in advance. I have to know about the Selmayr equation for that. So that's why people say, why not measuring that directly? But in fact, we have to go further, because here I am dealing with n minus and n plus, and when we measure, we are dealing with the principal nx and y and z refractive indices. So I would like to go up to the calculation of the angle, so that we see. So we have to solve this. We are in the YZ plane. I can precise. Here I have an x. This is the n minus. Very simple. So here I can replace and put nx. Okay. For this one, it's more complicated because it's with this and with this. So here we have an elliptical shape of the n plus. However, we don't need to go back to the Fresnel equations. We know how to write this. Ellipse, we know. It's a combination, in fact, this of nz and ny. So I can keep going just to see how is related the angle to the index and why we say that we should take care in this if you want a precision like that. It's not easy to see here, but if I go to the analytical expression of that is easy to get in this plane, you will understand why we are so sensitive to the 10 minus 4. So here I can write this. Here I have an ellipse. So if I have an ellipse, I should better write it like this. So this is n plus minus 2. We put the plus here. Okay, and this is a square cosine. The angle here is cosine, is theta, excuse me, plus this. I have, sorry, to multiply. I hope I will. So this is ny minus 2, and this is nz minus 2. Okay, so then I can replace this, for example. So I say this, Okay, so this is an x. So now I have to precise the wavelengths. This is lambda over 2. This is lambda. This is lambda. And then finally, I can isolate the angle. So I will go first the cosine square. So here you have a term that is alone for lambda divided by 2, minus this one that came from here, and z divided by 2 for lambda. And then you will isolate this one. And so it comes on the other side. So first you should take this one, and minus z of lambda, minus this one, and y of lambda. Okay, I hope I didn't make a mistake. So you can see here that you need precise value, but most of all, the angle is connected to the difference of the -2 power of the index that you are using. So small mistake you will make on this value if you are not precise enough. You will see how far calculations show how far we can be from the real result. I know that students, when they work with us, they always say, can you make the accuracy calculation? No, we don't need to make accuracy calculation. Just have a look here, and from this you see how the solution is very sensitive to these values. So this explains that why we have to be very accurate when using the Prisma method. And also, if you want to be able to characterize a process where the fundamental wavelength is 5 microns and half of this wavelength is 2.5 microns, this means, as you can see, that here the 2.5, the NX index at 2.5 microns, the NZ at 5 microns will be involved. And here also those two at 5 microns. So this supposes that when you made the Prisma method, you used these refractive indices, you measure those at this wavelength. Otherwise, you cannot say that you will calculate reliable phase matching angles. Okay, so the other approach is the direct measurements. So if you come back to the phase matching directions that are included in the gain, if we don't forget that we are working in low gain conditions, then the calculation of the phase matching conditions can be everywhere. This is a representation of the dielectric frame. So this is done for uniaxial, this is done for biaxial, and this is a shape of the free solution of type 1, 2, and 3 that correspond to free configuration of polarization. They are the only possibilities, as it was discussed, in the uniaxial. And this depends on the refractive indices values. What you see here, I underline, what you see here, this point is the solution of the K vector. This is phase matching condition. This is solution of the K vector that fulfills the phase matching conditions. Okay, and of course, it is easy to know that. Here it's more complicated. When you want to calculate, to measure phase matching directions, you see that I only draw one because there are many possible and they could be in different parts of the dielectric frame. You have to propagate in other directions and to fulfill phase matching directions as it is shown here. Okay, so you want to do direct measurement, why not? But then you have to deal with the whole, almost a lot of the dielectric frame space in 3D. And then what comes naturally for doing experiment is cutting the crystal as a sphere. Because if you cut the crystal as a sphere, then you are sure that you could reach any direction of propagation in the crystal. It has many advantages. First of all, we deal with characterization. We have new sample. The long crystal growth process has not been done yet. I mean, it's not, so often the sample is unique, as I said. So it's good because then you know that with a small, like a jewelry, small sphere, you will have all the information. So this is very compatible with the early stage growth of crystals. As you can see, all kinds of scale could be made up to today. So this is for BPM, biaxial, and DY cob. This is uniaxial negative BPM in CDSE, P2. This is BPM biaxial in BGSE. This is 3D AQPM in PPLN, the doped MGO. This is uniaxial negative also. Here you have a periodic polling that has been done in Japan, collaboration with the team of Takunori Taira. Here is the biggest one that we could have, 4.7 millimeter. It was provided by Valentin Petrov. Here is with our colleague Dimitri. Thanks to him, we could study LGT. That is it was not known before so much for, used for nonlinear optics. It is rather used for piezoelectric effects. So only one sample, and we get all the results. Okay. So if we want to work in planes, principal planes only, we could also make a more simpler shape, I should say. So here is the case of crystal cut as a cylinder for a work in the principal plane for BPM. Another one, it has been a great challenge because this periodic Pauling could not be made more in a thickness higher than it's 0.5 millimeter here. It's 5? 4. 4, sorry. 4, sorry. Yes, diameter, excuse me. I was speaking of the thickness. Yes, I lost mine. Yes, 500 thickness. I was speaking of the thickness, 500 microns and 4, sorry, a millimeter of diameter. And now, when working, because we don't have always big examples, so working with a partial solution that we know in the partial space, now we can also cut in the lab. It is Jérôme Debré who do that now. Bertrand Ménard did the sphere and the former cylinders. We can cut, as you see the dimension here, partial cylinders, a new one in collaboration with Antoine Godard from Onera. And this one was cut for use in device after this one was cut for characterization. So in one example, provided we have the good orientation device, we can reach all the direction for measurements in a small sample, as you saw the dimensions. Okay. So what is important is the shape. The shape has sphericity, that is delta D divided by D, the variation of the diameter compared to the mean value of the diameter, as you see, must be very good, and it is very good when it is shaped. It is polished to optical quality, so that it is like a sample you will use. Okay, we don't put coating, it is uncoated. And then the challenge is that the beam doesn't move. We have to implement the experiment. The beam doesn't move in the space. It could be one beam, and then if we are along phase matching direction, we get the output beam, for example, for second harmonic generation or another process. And then the goal is to be able to rotate the sphere along its center of symmetry. I would say the gravity, center of gravity, the middle. The sphere must rotate along the middle like that, okay? And the beam doesn't move and reach all the direction of propagation. Of course, we stuck the sphere, and sometimes we have to do one or two stuck, because here we have a lost part of the space. So we rotate the sphere, we tune the beams, and we access to all the direction of the dielectric frame. So this crystal that is used as non-effective zero coefficients sometimes, which involves non-zero chi2 element. And when we have phase matching, we have phase matching conditions. So we see an optimum of the conversion efficiency of the output beam compared to the input one. So I put input beams, I just draw one, because with one beam, we will do second harmonic generation. With two beams, collinear, we will do some frequency generation or difference frequency generation. So I will just finish before the break. I think I should, after the meal and the chocolate that we have at the end, the coffee will be good. So just to have in mind that the key issue, of course, when we do experiment, there is always a difficulty to overcome for the prism, for the precision of the data that you measure using the minimum deviation. With the sphere, the key issue is that everything should be collinear to the beam diameter, so that we control the direction of propagation and we control the corresponding phase matching direction. Okay, so but this is done, of course, using two lenses. The sphere is inserted at the middle of two lenses, and it is coupled to the beam like that. It doesn't move the beam. The sphere rotates, and we have filters after to select only the generated beam at the outside. So when we look at the shape, it is well known in high school, first high school optics book, that when you have a shape like that, and if the index is smaller than 2, then this sphere is equivalent to a lens with 2 focal points here. Okay? So if you come with a beam and you focus exactly at the focus point of the sphere, then you will be sure to propagate along the diameter. And this is a key issue. And then, however, if you don't do anything, when coming back outside the sphere, the beam will be divergent. And if you want that it gets inside the detector, that has usually a very small area, you have to make some kind of afocal, as is shown here, a device, to implement an afocal device, so that you get the initial beam waste outside the sphere method just before the detection. So the beams are tunable, they are collinear, their direction is fixed. The beams are focused properly on the sphere so that we don't blow up with the sphere, because if we focus here, we will burn the sphere, okay, and we will not control also the propagation. The sphere rotates on itself. The precision is, we are using a device that are used for X-rays, so they are very precise. The sphere diameter, of course, is smaller than the Rayleigh parameter, and the input beams are always in normal incidence. And what is important, I will draw it later, is that if you look at the propagation, there is no refraction at the input of the sphere. The beam goes straight, and after here, just have the effect of double refraction of the anisotropy of the crystals. And also we will see the advantage of having a second drop, a spherical output shape here at the outside of the sphere. Because we could have think about this and then going like a slab here, but no, there is a big advantage of making really something that is spherical at the input and at the output. Break. So, thank you for being back. Okay, so now let's see more about this sphere method that we have developed at Grenoble. I wrote it, I didn't say this is the idea of Benoit, but I was not with him. It was in 1989. Okay, so I have been working with him since 2001, I think. Okay, but still, this is an updated method that works very well, and we still continue to develop it. And in fact, the development is more from the detector point of view, because people want to make DFG in infrared, far infrared, and terahertz, as I will show you. So I don't know if you see well. This is a sphere, and this is the sphere under conditions. So I wanted to show a movie. We made it a long time ago with our former student in that time. So we use a tunable laser, and this is very interesting because to determine the idea of a crystal, we use a tunable OPO here with such crystals inside. So it's like some kind of a loop between the device, the crystal, and new device, and so on. So here is the input beam, of course, if it is 850, 1064, 1200, we don't see it. So here you have the card to see the input. And in this situation, it is not along the fast matching directions. However, if we rotate the sphere, you can see here the corresponding position mark out. And here, for example, we have the second harmonic generation of 850. So 425 blue. And in this situation, this is the extremal value of the corresponding conversion efficiency that is measured with a detector. Here it is silicium 1. And here also, a second harmonic generation means 532, and you see green, okay, directly at the output of the sphere. And also here, so more complicated because you have to see 600, and now you will, you see it, still see it, but it will be almost the end. Okay, after if you begin to continue to increase. So the only limitation, in fact, is the transparency range of the crystal. Because think about, there is no threshold for generated nonlinear optics. So the only thing you have to deal with is just put the gain you need, not to destroy the sphere, first of all, but just so that classical detectors are sensitive enough to see what you need. So in the visible, we work with silicium photodiode. when we don't want to record the value, just to measure the extremal. After we take in gas, above 2.5 for generation, and ENSB up to detector up to 5 microns. And now dealing with the terahertz, we just bought a bolometer. So our big issue right now is not a sphere, because we know how to make spheres, except that the material is always new. So the condition, hardness, and other properties are always specific, and the guy who is doing that has to deal with this to make a big one or a good one sphere. However, from the experimental room, the challenge for us is to have the good detection. So this is one experimental setup of the sphere, drawn here. We have many. I think now we have 4 or 5. Okay, so this is one with the nanosecond. This is the first one implemented with nanosecond lasers. So it is commercial one, which means that with one laser, the tunable OPO between 0.4 and 2.4, we can make the OPO alone here, we can make SAG. So this means that we can work in this transparency range, and we will take care between 0.2, so we should still be in the transparency range, and 1.2. And this commercial laser have all another beam which comes from the first pump beam. It is a link at 1.064 microns, so that usually when we perform SFG some frequency generation or DFG difference frequency generation, we collinearly send these two beams, one at this wavelength, the other one at the tunable wavelengths in the sphere. And then according to the process, we will select the photodiode. It works very well, and this laser is very stable. Also, concerning the orientation of the sphere, we have 2 devices. And as I told you, this is the same devices that we use for X-ray. So it is very, very good devices. This one is what we call the kappa geometry. So kappa geometry, we have very smart students who make program for us and could go to the dielectric frame spherical angles, so that we just have a computer and don't have to calculate, just ask for spherical angles and we go there. This one has the advantage that the sphere that is just stick here has just the part that is stick that is not accessible. Otherwise, you can access to all situations, all directions. The second example that we have right now that is implemented is using another kind of source, because new samples are more transparent than before. So now, according to new samples, this laser is tunable between 0.7 and 12 microns. And of course, used alone, you can make SAG between 0.35 and 6 microns, provided the crystal is transparent, of course. And always the link, as I said, at 1.064. Okay, and we could make SFG if we want to go to short wavelengths, or DFG if we want to go to high wavelengths. And remember that with DFG, we can have the scheme that we can use in OPO, PA, or PG. And this is a commercial device that we use. It's not an easy one. It is made of different stages. Since here, not only here, we deal with nonlinear optics. This is neodymium. This is the box for second harmonic generation and the third harmonic generation. Then it pumps an OPG. The link of the 1 micron is here. And since it is picosecond, we have to use a good delay so that they are together in a DFG box, commercial box, and from that we have almost between 2 something microns and 12 microns. And this goes inside the beam, the sphere, sorry. So I will try movies, but since I'm using a PDF, so I should do that. And I am with Mac. So, alors, the first one, I think I want to show you. So this is 2 students who were running at that time. So it is tunable, you don't see it, use the card. You see that there is nothing after and before and the beam is not in the visible. He rotates the sphere, of course he cuts the beam. And then close to the good point, you see that he could increase the blue because he is doing second harmonic generation of 850. And another student is recording the data to begin to, it was for the movie, huh? Usually they are alone. Okay, and now we tune the laser to the second 1.064, and immediately you see with the rotating stage, and you just take the good angle. Huh? This is manual. Benoit likes this one very much, because he is right in some points, because new students like the kappa, because kappa is automatic. But you have to be sure that you record phase matching directions. Huh? You could have a local extremum of the efficiency, and we have to really to be sure that it, and Aurélie. Elodie, thank you. Elodie, who is with us, knows a lot about that. Huh? Okay, I do it again just for pleasure. Okay, so it was in another lab where we were before. We are now in the Nel Institute. So the laser is tunable. We adjust the polarization with half-wave plate. We have the sphere. The propagation is parallel. The beam is no more than 40 or 50 microns here, and you rotate. You take care. Low energy, you don't need high energy, and you just, after you record the spectral acceptance to be sure that you got the phase matching angle. And you tune again, you don't see the beam. The beam doesn't move when it is tunable. And it is aligned first with the helium neon laser for security. Okay, and you keep going. And it is really direct recording of data that can be used as they are. Okay, you know now that you are working in the plane where the sphere is studied, that you can use this angle for phase matching direction. These data, you just take those 2 points, and you will have the wavelengths and corresponding angle. So, of course, as I said, the student like this machine. Okay, this is the other kind of kappa that you see that is automatic, huh? And the sphere rotates on place. Okay, I'm not sure here, but we did it. Okay, and you see here, you can access to all the direction of the sphere, and you have less place that is unused in this case. So 2 possible displays are used, and one have each specificity according to the studies that we want to do. Okay. The other room, because we have 5 rooms of experiment, 4, I think 4, not 5, but 4. 5 now, not 5, we got 5 last week, because we have also training of such experiment. So this is the kappa circle with the OPG, the large tunable laser, and always this sign is very important from the detection to be sure we have phase matching direction. This is 1 point, and for each tunability we have to select this point to get the spectral acceptance corresponding. And with the sphere, for 1 point we can make angular as a function of theta, angular as a function of phi, and wave, as a function of the wavelengths also when the direction is fixed. So the potentiality of the sphere method is that we input 1 tunable beam for SAG, 2 tunable beams for SFG and DFG. With the polarization control using half-wave plate, we can study all types that are needed. Of course, when dealing with birefringent phase matching, we have 3 types. When we add a QPM, we work in QPM device, we can work up to 8 types. We measure directly the phase matching angles, the associated conversion efficiency from the detection. We check the spectral and angular acceptances, and the only limitation is the crystal transparency range. And I give you historical, I will say, articles so that you can know in details what we are doing. And this is the last one that is waiting. Here are data. So this is data with cylinder. They were studied for DFG. Okay. So to convict you the difference between the direct measurements and the Prisma method, here in that slide you have the calculation that we performed using from the literature data of refractive indices that have been measured with Prisma. So you can see here how usually we are in agreement in the low part of the transparency range because usually people measure the refractive indices here. And you see here how we can be very far. Especially here you see this is what we measured and this is what has been calculated. So from our way of measurement, we do on the other way. As you can see, we measure directly the phase matching directions for a type. This is type 2 SHG. We can use them directly, but also we can interpolate this data because we know that phase matching conditions equation is analytical. And from our data, we can determine or improve or refine the previous Selmayrs that are plotted, that were used to calculate the angles. In continuous line, we have the calculated corresponding phase matching angle that have been found from interpolation of our data. So historically, it was done already in 2003 in RTP. It was the orthorhombic crystal that were used, like KTP, a lot in that time. And then monoclinic crystal came. So our monoclinic crystal here have been studied only with SAG, thanks to our new device that is transparent up to 12 microns. Then SAG is up to 6 microns, and this crystal is transparent not up to 3.5. So it was convenient only to perform SAG. More simple it is, and sometimes you get also very good data. So you see here how we could be far. I already showed you this picture. This is a calculation in dark from Prism, in black from Prism method. And this is our measurement as red points, direct measurement with the corresponding accuracy. And in blue, this is the interpolation of all data. We put something like 255 data in our computer to get very accurate new Selmayrs. And of course, I want to tell you that we don't measure all the processes, I mean the conversion efficiencies for SAG, DFG, and SFG. We don't use all types because this will be incredible. We select, we have a strategy that I'm going to show you. So here's the sphere, the collaboration with Takunori Taira group we made the sphere of QPM PPLN doped MGO. And it was great because before we developed in the group the theory of 3D angular quasi-phase matching. And with this experiment, this was the way to validate this theory. So as you can see here, in dashed line, or this is dashed line, this is dotted dashed line, dotted line, I should say. This and this are for Prisma method from the literature. 2 Prisma method here, and they do not correspond to our data. And in continuous line, you see the interpolation of our data that could help to improve the new Selmayrs. Again, here CSP. CSP is tetragonal, 4-2M, negative uniaxial. You have in red and green the Selmayr for Prisma method. In Kato, temperature was included, I think, in Kato. And this is our new Selmayr. So this is done at 21 degrees Celsius. This is our data. This study was not easy. And we got here, I improved the present work, the red one, which is closer than anybody. Here we have the first case of dark. You go to crystal, or I think it is interesting because we could measure up to above 9 microns of fundamental wavelengths, but the crystal seems to be, transparent up to 6.5 or 7, if I don't make a mistake around here rather. But we can measure because it is attenuated, but we saw it. And what happens is that crystal will become to be very transparent at higher wavelengths. They are not anymore in the visible, and they have very high indices. And because of that, it was the first case that we have to change. We had to change the focusing method because it is interesting because the focusing, the two focal points of the sphere when the index is higher than 2 are in the sphere. So when the index average, whatever it is higher than 2, it happens that you can show that the focusing points are here. So then at the first time we didn't know it, so we blow up the sphere, because if you use the usual scheme as I showed you, then you can increase inside the sphere, and we had to change, but we managed it. And here you see again, always with the commercial laser. Okay, as you say, I said to you, we don't measure all the situation, and our strategy is the following. As you can see, Prism here has been limited to this part of the crystal, of the transparency range of the crystal. This is N0. That could be solicited from the prism. This is NE, it is uniaxial. That could be solicited with the prism. And this is on blue with the sphere. By performing phase matching condition in SG type 1, we could solicit between 2.3, let's see, 3 micron and 8 micron, this index. And the corresponding one here between half, of course, 1 micron and 4 micron, something like that. And here, when we perform SIG type 2, you can see here the corresponding indices that have been used. And also, I told you when we perform DFG, we mixed 1.064 micron with a tunable laser. So, of course, we got the corresponding value of the indices at 1.064 micron. And in fact, the strategy is to be able, according to what you can make as all possible frequency conversion processes, is to be able to use all part of the indices. And more you will use the indices, and more your calculation will be available. So what you have seen here is that we could only use this. The other one are not used in the parametric process. So then we combine with this, and we improve the Selmayr equations in collaboration, in fact, with the Peter Schunman, who made the measurements that were very good in Prisma. Okay, so what's the goal then? When we have the ID, we make calculation, and we got the possible devices that could be used, the possible kind of devices. So this is an example of DFG tuning curve that could be used in a CSP OPO scheme for different types of configurations. That means for different combination of polarizations. And you see the two kind of devices that are very interesting for people right now. The first one is this result. This result here shows that the angle is almost the same here, limited to 43 degrees here, almost the same, and by orienting a crystal in this direction only, you got an emission between, let's say, above 3 and up to 7 microns. So this is what we call the supercontinuum. So this is good because if we have very good calculation based on very accurate measurements, then we can give very precise situation of use of crystal. And this is the use of CSP in this configuration for supercontinuum generation. And of course, here we could reach the same part of the tunability in the transparency range of the crystal with another possibility here. Here you see that you could see the same range of emission, but in this case the angle has to be changed between 55, almost 56, and 90 degrees. So in this case we can use the crystal cut as a cylinder or even a partial cylinder because we have only 35 degrees of rotation to do, and then we can propose a continuous tunable OPO here by rotating the crystal. And this now is made. Okay, now the current work, LGT, I said, has not been studied for nonlinear optics. However, it's a crystal that is grown by Shokrasky method, and then you can have very big aperture of crystals. So that means that if you are concerned with the damage threshold, if you put very big size of input beam, you could remove, the problem of damage. You could manage the problem of damage threshold. So here you can see direct measurement again. This is the work of Elodie. That's why I show here. This has been, we were spending a lot of time doing these experiments. And it is interesting because by using the 1.064 micron beam and tuning it with this one, No, sorry, we do need it with this one, 0712, this is not 12, but this part, in fact. Yes. So then we made a DFG, and we could show a generation between 2 and 6 micron, and we stop here because this is the end of the transparency of this range, of this crystal. The crystal is transparent up to 6 micron. And you could see here, we could see that in fact, if we want to use this in the OPO, the most suitable pump beam, the pump beam is not 1.064. It is rather in this range. That means that we are working now to use this crystal and pump this with wavelengths corresponding to this. And then we are thinking about titan sapphire laser. That's why Elodie look at what kind of experiment she had to do, and she did all these kind of experiment so that she could cover all the wavelengths values of the 2 indices that are involved in this uniaxial crystal. She was only limited by this range, and she performed calculations, and she used an optimum, here you can see here, of supercontinuum generation with the crystal pumped at 0.964 microns, and she will do the corresponding experiment in Bordeaux next month, because it is interesting for us to give the idea of the crystal and to test it also. Okay, now let's come about the walk-off. Direct measurement of the walk-off. I'm not sure you will see that. It will be very nice in the computer. Do you see a double holocone, double ring? I'm not sure, it's too dark. Okay, you see it, double ring, Sam? Okay, this is really nice because this is what happens in biaxial crystals when the light propagates along the optical axis. And people like to use that a lot now for laser configuration in biaxial crystal. So here you have the signature of the walk-off related to the index surface. As I told you before, if you run experiment in these directions, the Poynting vector propagation direction will not be the same as the direction that you selected in the crystal. And this is due to walk-off. And the consequence is that if you think about that from the theoretical point of view, in fact, here it is not 0. It has a value. This means that one beam that sees, because it is polarized, it's top view. The beam that is polarized vertically will see this layer of the index surface. No walk-off because it is circular. The beam will go straight. If you add to this horizontal polarization at the income beam, then the second light will see this layer that is elliptical. And because it is elliptical, there is walk-off. And the consequence is that the output of the beam, at the output of the crystal, I'm going to explain that to you, you will have 2 beams. The beams are polarized orthogonally. This one corresponds to this. This one shows this layer. It has seen this layer. And if you are along a main axis, of course, whatever you use, if it is an elliptical or circular layer that you are solicited, then you have the 2 beams that are together. And if you are able to propagate here, especially in the XZ plane, you will see this, then 2, then the double holocone, then this and this. Now, the point is how to measure that. So people explained that long time ago in the slab, except that if you want to see that, because walk-off is very small, if you want to see that at the output of a slab, the slab should be very long. Otherwise, you need a loop or a microscope to see what happens, to be convinced that you see that. Why? Because if you see a slab like that, look at this. This is refraction related to the direction of propagation. There is no refraction. And here what you see is the pointing. Otherwise, the K vector is not moving of direction. So there is no refraction at the entrance, no refractions at the output. And then the only possibility to see the separation between those 2 beams is to have very long crystal. And this is not the case when you make characterization of new one. However, look at this is the top view of a sphere. That could be also that of a cylinder. Here, like here, you come in with on normal incidence. So the beam that is perpendicularly polarized, it is a top view, will see the ordinary beam in this plane. And then the pointing and the K vector will be the same, no refraction at the input or output. However, the beam that is horizontally polarized, we see the elliptical layer, and then in this case, there will be refraction at the output, because for no refraction, we should propagate crossing the center of a sphere, and we are here. And this is important because you have refraction here, because k vector is like that, and because of that, the beam will change direction at the output. So that's why I say you see that like the finger in the middle of the noise. Sorry, in the middle of the finger. So I say that because even at some millimeter, centimeter after the sphere, you will have the direction here separation. And if you are at 1 meter, you see them very well. So these two beams are perpendicularly polarized, and if we measure with the camera the distance between these two beams, the limitation is the pixel, the size of the pixel of the camera. So if we measure this distance with a very simple and accurate geometrical calculation, we can get the determination of the raw value in the crystal. This is done in the red with the helium neon laser. This has nothing to do with nonlinear optics. This is done very precisely because it uses a continuous laser. This is linear optics, okay? And this is the sphere that you can see here. Some centimeter after the sphere, the output, the two beams, because the sphere is like a lens. There is a magnification of the effect at the output of the sphere because there is refraction at the output of the sphere. So you see the direction here. You see the two output beams. They have been lighted by nitrogen. And unfortunately, I don't think you see here, this is a double holocone. So I'm going to try a movie. But first, because that, I want to see, of course, the result of experiment. Here is the result of experiment. We work in dielectric frame of Y-cup sphere. This is shown here, and you can see how, by following the distance between the two beams, we could determine the walk-off value directly, and we could compare to the calculations that are analytical in the principal frames. Okay? And this is done in the XZ plane, and normally you have an optical axis, and you should have this double ring, but it is so located at a specific angle that you can see that it doesn't alterate at all our data. I'm going to show the movie. Fortunately, we don't see us because it's a long time ago. We were young. So here you see the beam alone. Even polarized, we don't see it, one beam. Now we put the sphere, and you see any direction, two beams could be seen. You rotate, two beams. Now one beam, you know you are along a principal axis, two beams, and so on. We put nitrogen so that we could see the propagation output the sphere, two beams, one beam. Of course, don't do that, as Yannick did. Don't do that. Okay, so two beams, one beam. And sometimes when you reach the optical axis at the output of the sphere, you will see then the double ring. First of all, we wanted to show you that these two beams are related to the two layers of the refractive indices. The two layers of the index surface are linearly and orthogonally polarized. You can see that. If you use a polarizer, you see that very easily. And now let's go to the optical axis, I think. And because the beam is diverging, this is the reason why. And because the sphere also output is a diopter. You see it? I don't know if you see it. Double ring. You see it or not? Yes? Yes? Okay. So, and if we remove, so you see polarization is linear. The scheme is very special. If you rotate, this is, you kill, I should say, one state of polarization that is orthogonal, because this is made by the two output beam related to the two layers that are combined in this special. And less than 0.5, 0.3 degree, you lose it. So it is very precise measurement of direction, if you use that. And think about that, it is if you draw it in a quarter of a plane, you see it, okay? But in fact, what happens in the quarter of a plane happens 4 times in a full plane. So here, if I come back in the biaxial crystal in the X Z plane. Here I have ny. Here I have nz. Okay. Here I have nx. Should begin here. And here I have ny. So this is a circle. This is the ellipse. This is the optical axis here. Okay. But if you go on the other side, what is circular, excuse me, it's difficult for me to draw it, but with circular happens on the other, this also. So in fact, if you, I should do like that, okay. It should happen. Now we are not so used to draw. Now we make PowerPoint, this is not good. So what I want just to give you as an idea is that if we rotate in the full plane, we see this, and the precision is plus or minus 0.2 degree. It is very sensitive to the direction. So we use that. We use that because with this, it is the way, in fact, to have the position very precisely of the main principal axis of the dielectric frame. It is very precise. In fact, with the sphere, we really see the index surface, and we can make the difference. We can say if what we see is x or z. We know exactly the position of the axis and the name. Okay, now I'm done, I think, with the walk-off. Now, from gain to nonlinear coefficient values and sign. Okay, so again, we open our virtual books, web books that we have now. And let's, as I said, we are dealing with low gain because we are making a characterization. Also because the main parameters are involved in low as well as in low and high gain almost in the same way concerning the expression that you have here. And to be sure that we get gain, we perform angular or end spectral acceptance when we get what we suppose to be a phase matching point. And of course, before to do experiment, and we can say, well, let's run, let's put the laser, let's put the sphere, and let's make the experiment. We have to make like small calculations because think about that we are dealing with nonlinear crystals with symmetry, and that means that we have not all the 27 elements of the Chi2 tensor that are involved, only some of them according to the symmetry, but also we have limitation of solutions because in the effective coefficients are also involved the state of polarization of the free mixing waves, and we have to, there are limitation of solutions, and we have to deal with type 1, type 2, type 3 in birefringent phase matching, and up to type 8 with QPM devices. So two methods here also are proposed. The one is phase matching direction, so I will get to it directly because we can use it with the sphere, of course. And the one that is a lot used by people, in fact, is out of phase matching conditions. So as I said, we have to perform calculations to be sure that we'll see something in the directions we will work with. So everything is analytical in the planes. Out of the planes, we can manage now with numerical calculations. Here is the case of CSP, very easy, tetragonal, uniaxial, by chance, only one element to determine. We run these equations, we find the solutions, and we know, in fact, where we should work to get this element to be measured. There are many possibilities, of course. And for example, we see that for DFG type 2, if we select phi equal to 45 degree, then 45 times 2 is 90. You can have a maximum value of this along theta directions. And here in this situation, here if you put phi to 0, you will have maximum effect, and you could measure this along phase matching directions. And unfortunately, what you have here, take in mind, is all possibilities, but solutions here are only phase matching. So that is not why you have this element. You say, great, let's put the phi, for example, here to 45 degrees. I eliminate this one. This is equal to 1. Let's run with this. So you say, well, let's go to a 90 degree. Great, I should get this element. However, you could have no phase matching directions at 90 degrees, and then it doesn't work. Okay, so you have to select and to deal with this before making experiment. So this, you have one element, so only the value to determine, but when you begin to work with biaxial, then there are many elements that are involved in fast matching direction. And then comes the discussion about measuring this, means to deal with all these equations, but also with the fact that several elements could be involved together, involving their value and their sign. And so what about the sign of the nonlinear coefficients? So I try to work on KTP. So let's work about the sign. Let's be first in planes. I took these equations. I took KTP, that is orthorhombic MM2. I am in the following assumption. And from the table, from Benoit lectures, you will take all these elements. And then you combine the fields. You know you are going to do type 2. This could be only this. This and this. These are both this one. And then you check. You check what is possible. There are many possibilities for the combination of those three fields that I call the field factor. This is commutative. You can put this one before and this and this and this together. Just don't forget that this is one is for 2, for 1, and for 3. And then you have a look. For example, can I solicitate, if I do this kind of fast matching, will I use this? This is true. If for E minus, I have Z. Because it corresponds to J. For E plus here, I have, for E minus, I have X, yes. For I have Z, and for X, I have K. K is X, I is Z, and J is X. And when I see that, I can see that some are involved, some are not, some are involved, some are not, and I can determine that way the corresponding nonlinear coefficients. Okay, and I can see that if I work suitably with the sphere, I could use this one only, or perhaps this one only. But what happens is I use both. It is very interesting if I use both. Because if they are opposite sign or same sign, the result will be difficult. And this is the only way to determine the sign. So let's see the results that Benoit proposed a long time ago. So this is the result for KTP. Now it is worked out of the plane, so the results are just numerical. Let's look at performing type 2. This has the advantage that we work with one wavelength, and we check for all direction of propagation. And because of the linear properties, we see what is possible only, provided that these directions are fast matching directions. And you see that here you could solicitate close to 0 only this chi 224 element. And here you will solicitate, because the others are very weak, almost 0, even 0 here, only you could determine the value of chi 1,5. But here you could determine they could be together, the two elements will be together in this part, and then you could check the sign of those two elements. And there was a big discussion between chi 15 or chi 24, they were called, or D, it's just a half 0.5 between the chi and D. So are they of the same sign? Then you should have this continuous line. Are they of opposite sign? Then you should have this dashed line. And the data through the sphere gave directly the result. Okay. Now, concerning the values, well, you can do that with the sphere, but you should better go to using slabs cut in the good directions on fast matching conditions. So once we have defined the fast matching directions, we could slabs in the suitable fast matching directions so that we could solicitate what we want to measure. So here is an example of the current device that will be published soon. No, it has been, the one I'm showing, sorry, it has been published yet, not so far ago, I would say. And you can see here the device. You need to take part of the input beam, part of the output. You have to work hard on the detection so that it is weak because you have low gain, that you can see it. You have to put the tunable laser and to want the measurement. And when you want a measurement, you want the value, you know, everybody knows that making an absolute value measurement is very, very difficult. You need to be aware and to control very well the beam's size and the transmission of every element. So what is usually made is that people will use a reference. KTP is very well known. The coefficient of KTP is very well known, D24. So we cut a KTP crystal in the same direction as LGT so that, I mean, same direction for the same, almost the same generation of wavelengths, so that you will not analyze the tunability of the transmissions, of the device, and then we could make very accurate value measurements of the DO coefficients. For this crystal, there were only one, like for CSP. If there were many, we could have used the sphere for performing the sign of the nonlinear elements. So what I have to say that here now, because we have been working a lot on this problem, is that it is very difficult to be sure it is phase matching, and we should really perform phase matching wavelength as a spectral acceptance, but also angular acceptance. And then, as Benoit said, we are sure. Okay, so there are other ways that people use a lot. Non-phase matching conditions. Someone already talked about the Maker fringes technique. Okay, so it is very well known, as well as the formula, then the analysis. And what I should say here is just that it is non-phase matching conditions. So the signal is very weak, and what you will get is only the absolute value of the effective coefficients. Okay, and otherwise all polarization schemes are possible. So this is the way to measure the key ZZZ if it is non-zero in the crystal, like in KTP-MM2. However, it is in non-phase matching conditions, and you have really to implement very precise device, as Ishiro Soji did, for example, to have reliable data. Also, the other way, of course, and you are dealing with the coherence length, so you can translate a prism, crystal cut a prism, and then you can get also the same kind of data in non-phase matching conditions. Okay, just a few words, good, before I go to the two last parts. As I said, to do all this, sphere, cylinders, slabs, you have to control the orientation and shaping of the crystals. So this is the way we work in our lab. We receive bulks, and they are shaped, and they have to be oriented in the the dielectric frame. Okay, and from that, we use, in fact, the crystallographic frame first. Okay, so this is the crystal. It is polished. Okay, it is shaped with the commercial device, and this is the kind of result. And what is very important, of course, is the orientation. Very, very important. This is the spatial shaping that has been implemented in the lab for making a very nice partial cylinder. It's not easy. You have to control the sphericity here. So we made all the people would have made. We made a wheel. So first we make a square. We have our sample, that is a slab rectangular. We put two other samples that have nothing to do with nonlinear optics. We make a square, and then we work on this square so that it begins a cylinder, because this is the best way to make something very precise. And then we unstuck the part that we don't need, and this is the best way to make partial cylinders. And we develop in our lab, Jérôme Debré, a special tool to do that very accurately, so that the shape here is perfect. Okay, more details about the device that is used in our lab, and more details about what we can get as a cylinder that can become also a partial cylinder. Also, we have to deal with crystallography, so we use Laue X-rays, backscattering Laue geometry. This is very important to know about the quality of the crystal, and also about the orientation of the crystallographic frame. We combine this with conoscopy. So for this, of course, we use the polished crystals, very good quality shape. Conoscopy pictures are optics, so you can get symmetries. You will not get the name, of the axis. You need more work. However, you will get symmetries, and by combining that, first of all, whatever is the situation, you can determine before working the orientation between the crystallographic frame, that is the best way to make the shape oriented, and the dielectric frame where you want to work. Here is the crystal shape, 6 faces. This should be accurate. With the sphere, we don't need this. With the sphere, we cut the sphere. We just need the sphere. And then we just use, if we want to work, just stack it along. So the sphere is like that. We want to work like that. So we can stack it along a crystallographic axis. We will have all the 3D after because we know where is this. And then we can stack it with the crystallographic axis inside the plane. It's more simple, not so complicated, because after, with the sphere and the walk-off, we will know where is the dielectric frame. Break.